Okay. All right. Everyone's coming in.
I didn't realize I looked at the for
Bring
you.
him in. All right, I'll wait till they're all, it says they're all in. Okay. Hi, everybody. Welcome to tonight's, well, at least tonight here in the East Coast. It's still the afternoon on the West Coast where Bridget is. Europa Clipper Mission review from with our panelist Bridget Landry. Bridget was she's worked at JPL for a very long time, although now she's not there. But she's going to be telling us all about the Europa Clipper mission. So if anybody has any questions, we are going to wait and hold them off till the end of the presentation. So to queue them all up, if you have questions, please put them in the chat. And I will make sure that they all get asked at the end, because we will have some time for Q&A. So I'm going to turn this over to Bridget. Thank you, Bridget.
Thank you for having me.
Yay.
I'm glad I actually showed up this year.
It's okay. We take turns. We have the other scientists didn't show up this year, so it's like, yeah.
Yeah.
It happens. It happens.
Yeah. Yeah. Well, last year I was still reeling from having been laid off, so I wasn't firing on all cylinders. So anyway, my name is Bridget Landry. I've worked in spacecraft operations for years, and I find the Europa Clipper mission very interesting. I wish I had had a chance to work on it, but I have several friends who are. So I will give you what I know about it and a few stories from my friend who is in charge of the radar instrument. So moving on, this is a spacecraft, and this doesn't show you very, it's hard to get a feel for just how big a spacecraft this is. But some of the pictures later will show you that. We have a magnetometer boom. It has to, the magnetometer instrument has to be way out on a boom so that the spacecraft itself doesn't interfere with the data. We have a high gain antenna. You'll notice it does not deploy. We learned something from Galileo. So we have the two engines, and this is a solar powered spacecraft. Now, back in the day, we didn't make solar panels big enough to power something at Jupiter. Juno and Europa Clipper both are Jupiter orbiters, and they are solar panels because we've increased the efficiency and our ability to make larger solar panels. So you know, this is an example of how we're improving what we're doing. There are two different radar sets of radar antennas. We have a whole set of forward pointing instruments and a whole set of downward pointing or nadir instruments. So, and they also fall into two categories: remote sensing and in situ. That is, looking at something far away and testing things in a region around the spacecraft. We have a UV spectrometer. We have a narrow and wide angle camera, an IR spectrometer, a thermal imager, and the reason instrument is the ice penetrating radar. The reason that's important is because Europa is covered with a shell of ice. However, from previous missions and from other observations, we have determined that there's an ocean underneath this ice, and that ocean sometimes comes up through fissures in the ice and smooths out the surface. You get resurfacing, just like Earth doesn't have all that many craters, whereas the moon has tons. The reason is because Earth has atmosphere and weather, and it weathers those craters, and they tend to disappear. We were very surprised when we first got a close look at Europa that something like that was happening on the surface of Europa, and it was eventually determined that it was some of this ocean water coming up and flowing over the surface and then freezing, so it would resurface Now, the in situ instruments are mass spectrometer, a dust analyzer, a magnetometer, a plasma sensor, and a gravity radioscience measurement to measure the tidal flexing. The reason that this moon can have ice under or water underneath the ice is because of tidal flexing. The pull of Jupiter and several of the other Galilean moons flexes it, and that adds enough energy and heat to keep some of this water liquid. This is the plan of how we're going to get to Jupiter. We launched in October of 2024, and I've got some stories to tell about that. And from Kennedy in Florida, and we are going to be cruising and arriving at Jupiter in 2030. Now, that may seem like a long time, but that's only 5 years, whereas Cassini had a cruise of 7 years. So, but it's not Mars, which is usually about 9 months. So, you know, you got to pick and choose your planet. Anyway, we launched from Earth. We are going to go for a gravity assist here shortly, like next week. We're going to swing around Mars. We're going to come back around Earth, get another gravity assist at Earth, and that's going to shoot us all the way out to Jupiter. Back in the day, we had a big booster. Some of you may remember the Saturn V. We don't have that anymore. And that's why we have to do these very long, complicated pool shots to get to the outer solar system, because we just simply don't have a big enough rocket to go straight out. So that's why you get this leisurely tour of the inner solar system on your way to the outer solar system. So it was, we actually did launch on the 14th of October. And as I said, there's some stories there. The plan for this mission, and this is something that I didn't really understand until I was on Cassini, and that there's a difference between a tour around a planet and an orbiter around a planet. While we will be in orbit around Jupiter, it would be extremely difficult to be in orbit around Europa. We will not be covering the same ground. We're not going to be, it's not like Mars Reconnaissance Orbiter or Mars Odyssey, where we're covering the same ground every 14 days or whatever. This is like a really complicated pool shot where we're using the various moons to adjust the trajectory so that we can get shots of the top of the moon, shots at the bottom of the moon, shots of the leading edge, shots of trailing edge. And I'm just really glad I'm not on the nav team, because those people are under a lot of stress to get this to work right. But flying by some of these other moons is how we change our trajectory enough to get these good shots of Europa without spending tons and tons of propellant. We're doing about 50 low altitude flybys over the 3.5 years of the main mission. But we're hoping for an extended mission, in which case we can fill in some of the gaps. And it makes us think of the whole Trek episode. So this is the science that we always have. We have this set of instruments, but they're trying to answer specific science questions. And one thing we want to study is the ice shell around the moon and the ocean underneath, and how those two interact. We want to understand the composition, not only of the ice shell, but of the ocean and the any other materials that we see. This is this image is stretched, but there is definitely color differences which suggest composition differences. Sometimes color differences are a factor of texture differences, but from some other data we have, we believe that these are compositional differences, and we want to study that. We call it geology, but it's more like iceology, because this is not rock, this is ice, and it moves different than rock would, but it is one of the aspects of it, the physical changes of the ice. And the activity, as I said, the interaction between the shell and the ocean, and we see geysers on an occasional basis, whereas Enceladus around Titan, we see almost continuous geysers. On Europa, it's much less frequent. And there is hope that at some point we can land on the surface of Europa. And so part of what we will be doing is taking high resolution images of this surface to try to figure out where might be a good place to land. Because you don't want to land too close to a crack and go whoopsies and take a dive, but you also don't want to go land too far away, because then you're not going to get the sampling that you want. So I haven't heard rumors of rovers, but we do a lot of rovers, so who knows? The reason we're interested in this is because everywhere on Earth we find water, we find life. Doesn't matter whether it's super cold water in the Arctic regions or acidic hot water near ocean vents. There is life in all of that water. So that's one of the things that we're hoping to determine is there, because we see from the spectroscopy and the spectrometry of what we've done so far, we see a lot of the elements that we need, elements and compounds that we would need for life exist there. So, and there's, as I said, the tidal heating that's putting energy into the system, and it's been simmering for 4 billion years, and life showed up here much sooner than that. So it's just something we want to know. Okay. Trina put a lot in here about, what I mentioned was, I stole this from my friend Trina, who was on the radar instrument. And this is the first time she's been on the development end of things. And she had a lot to say about that. And she's not going to be doing that again. That's not where her strengths lie. So some of this is her, these are the phases that we go through. Phase 3 is actually assembling the spacecraft and making sure that the pieces talk together. And then phase 4 is environmental tests. We put it in vacuum, we put it in high radiation, we put it in hot and cold, and shake it all around. My nephew actually runs that lab, and they play heavy metal rock sometimes as part of the vibrations. So, and then after all of that, they take it all apart again and then do the final adjustments, and then they assemble it all in what we call ATLO, assembly testing launch operations. And they were aiming for this for the launch window in October of last year. Why is it in 25? That's weird. Okay. So moving on, but you can see these the red hash marked line. That's when people are having to work on Saturdays. The pink hash marked lines is when they're having to work on Sundays too, and red is when they're doing 2 shifts. Part of this was because they laid off 8% of the lab in February when they were launching in October. And everybody on Europa Clipper thought that they would be protected because they were launching in a few months. And not only did they hit the Europa Clipper team, they hit the hardware team. Now, the last few months, the last 9 months before launch, is crazy, insane work for all the hardware people, because this is your last chance. It's got to work, and it's got to work by the time you close it up in the space, in the launch rocket, and there's nothing you can do after that. That is your crunch time. And the fact that they laid off people on the hardware team during that time period was just stunning to everybody at the lab. It was horrific. And that's why you ended up with people working double shifts, Saturdays and Sundays. It was really horrific. This is just more about the environmental testing. Not forwarding. There we go. This is the big vacuum bay that we put the spacecraft in to do all these tests. And we actually have several sizes of bays, some for smaller instruments, some are smaller spacecraft, and some for just testing specific instruments, and some for small spacecraft like Pathfinder, and some for larger like this. So we have a whole suite of these vacuum and vibration test chambers. This is part of the magnetometer testing. And the thing is, the magnetometer boom is so long, we couldn't deploy it in the bay. So we just had to test what parts we could and hope for the best. Hope we had really good engineers. This is how we shipped it. It was put on a truck and taken to a large Air Force plane. We used to drive them across the country, and people would shoot at them, use them for target practice. So we fly them now, because this is why we can't have nice things. So then offloading at KSC, getting ready to launch. Then this happened, that the chips that were used on the spacecraft were, several batches were found to be defective. And this is July of last year, when we were launching in October. And so what they did is they pulled the people they needed to investigate this situation, and they told everybody else on the team, ignore it. There's nothing you can do. Just keep doing what you need to do. Remember, these are people working 2 double shift days, 7 days a week. And they said, just block it out of your mind. Just don't think about it. It's not your problem. Move ahead as if we were going to launch on time. Because if we don't do that and we find out that we can fly with these chips, then we're hosed. You know, if it happens that we do all of this work and we have to take it all apart to replace all these chips, and that would have been a 3-year delay, then it would happen. But they had to proceed as if it was going to be okay while they did the analysis. And what they finally figured out was that if they heated the chips after every dive through the radiation belts, that would cause them to recover, and we would not have issues. And apparently, when this first came up, one of the engineers went to the higher ups and said, you know what we need? We need to put one of each of these batches in a box on the outside of the spacecraft and use those to test so that we know that they're okay. And they all said, thank you for your input. Let's, go back and do your work. So of course, in his one downshift a day, he cobbled together this box. And 3 months later, when they came back saying, "Holy shit, we need that box you talked about," he said, "Here it is." So this is the kind of commitment that people have to these missions. You get so involved with it, and you just, it becomes so much a part of you that you will do anything you can to make it succeed. And it's just the dedication of some of these people is just amazing. So then we're now scrunching up and using up all of our margin time. So we started out with like 30 days of margin here. Well, now we're down to 7, and we're down to 7 here, and that was about 10. So and again, we're working 7 days a week at that point, and it's getting really kind of scary. This is really exciting. This is as I said, Galileo taught us that having things that have to deploy is really kind of scary, but there was no way to ship these solar panels to deploy. You had to have them folded up inside the rocket. So that's just one set of solar panels. There's a whole other set on the other side, and that, see just how big those things are. I don't think the radar instruments are on. Anyway, but we, they could only test, again, they could only test one set at a time because the bay was too small to hold it all. It's when it's fully deployed, it's bigger than a basketball court. So it's not small. So this is it all folded up, and you can see this fairing around it that's this part of it, encasing it and protecting it from anything in the atmosphere or space dust or whatever during the actual launch. And then we're launching for Florida. It was October. And the first Category 5 hurricane in a long time was literally going to pass over the launch facility, the actual launch pad, 45 minutes before we were supposed to launch. Needless to say, there was a delay. And Trina has some lovely stories about what it's like to be in a hurricane and watching tornadoes spin off from the hurricane. And sounded like an interesting no shit, there I was story, but I'm not sure I really would want to be there. This was the carport of the hotel she was staying in, and the bank across the street that was destroyed by a tornado that was spawned by the hurricane. So yeah, interesting times. Now, post-hurricane, the weather was gorgeous, and they only delayed by 4 days. So that was they had a clear sailing after that. Okay.
Live at NASA's Kennedy Space Center for NASA's Europa Clipper mission, a nearly 2 billion mile, 5.5-year journey to Jupiter's icy ocean moon.
And liftoff. Liftoff, the Falcon Heavy with Europa Clipper, unveiling the mysteries of an enormous ocean lurking beneath the icy crust of Jupiter's moon, Europa.
Side booster separation confirmed. fairing is separated, and those will be recovered by SpaceX's own recovery ship, Go Cosmos.
This is a big moment for the program, for NASA, APL, and JPL. Let's watch.
Europa Clipper, separation confirmed.
And there you go. NASA's Europa Clipper probe, embarking on a long-awaited mission to study Jupiter's icy moon Europa. And what a sight.
Now they wait for acquisition of signal.
And I believe we have it.
Right.
There it is.
Flight, this is
Confirmation of signal from the spacecraft Europa Clipper.
So that was pretty exciting.
Live at NASA's Kennedy.
And that's just a still shot of the launch. Now this is something that a lot of the spacecrafts do. It started with Voyager and Pioneer with the record and the plaque. And every spacecraft has some sort of message. Sometimes you can sign up and have your signature put on the spacecraft. Sometimes there's recorded messages. And this is the one that was on, that is on Europa Clipper. It's a poem by the poet laureate at the time, Ada Limon. And I believe I want to just say that there was a physical representation of the sound of her reading it, but I won't swear to that. Like the record. But
In Praise of Mystery, a poem for Europa. Arching under the night sky, inky with black expansiveness, we point to the planets we know. We pin quick wishes on stars. From Earth, we read the sky as if it is an unerring book of the universe, expert and evident. Still, there are mysteries below our sky. The whale song, the songbird singing its call in the bough of a wind-shaken tree. We are creatures of constant awe, curious at beauty, at leaf and blossom, at grief and pleasure, sun and shadow. And it is not darkness that unites us, not the cold distance of space, but the offering of water. Each drop of rain, each rivulet, each pulse, each vein. Oh, second moon, we too are made of water, of vast and beckoning seas. We too are made of wonders, of great and ordinary loves, of small invisible worlds, of a need to call out through the dark.
This is the plaque, the actual plaque that's on the spacecraft, and you can see it's got the poem on it. It's got directions of where Earth is versus the Europa. Don't remember whose face that is. What? Sorry about that. I thought I knew. And these are all written representations of various languages speaking the word water in all of these different languages. So that's kind of cool.
3, 2, 1, engine ignition.
There's a legacy of NASA spacecraft carrying inspirational messages from Earth, going back to the Pioneer plaque and the Voyager Golden Record. Now, Europa Clipper, a new mission from one ocean world to another, will continue this tradition. Because water connects our planet and Jupiter's moon Europa, all life as we know it, and all human cultures, a part of the spacecraft has been engraved with designs inspired by water and human connections. This metal plate is part of a structure that will protect the spacecraft's electronics from the threat of Jupiter's radiation. On one side of the plate is a design we call water words. These rippling lines represent recordings of the word for water in a diverse collection of human languages. The other side of the plate is a montage of elements that complete our message in a bottle. At the top is the Drake equation, a tribute to the visionary idea that the probability of finding life in the cosmos is something we can estimate. Next, these two lines represent radio frequencies emitted in space by molecules related to water, which have been considered an ideal place to search for interstellar communications, as suggested by some researchers. They represent our ability to use the language of science to search for signs of life. Next is a portrait of one of the founders of planetary science, Dr. Ron Greeley, whose early efforts to develop a Europa mission laid the foundation for Europa Clipper. At the heart of this message in a bottle is a poem in the handwriting of U.S. Poet Laureate Ada Limon. The poem connects the two water worlds. Earth, yearning to reach out and understand what makes a world habitable, and Europa, waiting with secrets yet to be explored. Finally, the bottle, orbited by the 4 largest moons of Jupiter, to which will be attached a microchip etched with more than 2.6 million names of those who signed on in the spirit of the poem as our message is sent on its voyage to Europa. As technically advanced as the spacecraft is, every part of it is made by people. And all of the markings on the plate are either handwritten, hand-drawn, or represent human voices and names. Because exploration
Liftoff.
is something we do together, something that connects us all as we head out into the cosmic sea.
Okay, I got most of it right. I just had the diagram wrong, and I forgot the Drake equation. Oh, and that's Trina holding the backup copy of the anchor plate. Oh, and this is where on the spacecraft this plate is mounted. And one of the things that I think is really cool is that all of these missions inspire artists. And JPL actually reaches out to these people and commissions some of this. This one and this one were part of calendars that we got for, we get a calendar from JPL every year. And they had these images of what it would be like to vacation. That's, you know, science fiction images of vacationing on all of these various either extrasolar system planets or moons or other planets in our solar system. And it just, I find this is inspiring, and it allows us to reach people who might not otherwise be interested. I was part of a sewing circle, and one of the women told me that she had never been interested in space until she met me, but that my enthusiasm and my, you know, triumphs and failures and what brought it closer to home, and she started to understand the value of it and appreciate it in a way that she hadn't before. The story from when I was on the Mars Pathfinder mission, there was a big sale at Joann's, and I was at the sale, and of course we're standing in line to get to check out, and I'm talking to these ladies ahead of me, and they're buying fabric for quilts. And so I was talking to them, oh, my mom's a quilter, my sister's a quilter, and so they asked me what I did, and I said, oh, I work on Mars Pathfinder, and they went, oh, say hi to Yogi for me. And I knew then that we had done something that not many other missions had done, is we had broken into social groups that hadn't really paid attention to space programs before. And so when you take attention from quilters, when the quilters know who you are, and it hasn't had anything to do with quilting, then you really have penetration of your market. And so that was really kind of a pivotal point for me to really understand how this kind of outreach can be important to the program. And these are the same people that, if we get threatened with something being canceled, these are the people that are going to call their congressperson or write a letter or write an email or send a text. And that's important. It's very important for government to understand how bonding this all is, even for all of how we are not liked in a lot of places around the world. They love our space program, and they love the fact that we share it. The data comes down and we give it away. And not everybody would do that. And so it's one of the very few things that is universally appreciated around the world about the US. So that's my bid for the space program. Okay, the solar panels have deployed successfully. The radar antennas have deployed successfully. The mag boom has deployed successfully, and we're all breathing a huge sigh of relief at that point. So we're on our way, and things are good. As I said, we're doing the Mars gravity assist next week, so we'll be in the news for that. So cross your fingers for us. Eat your lucky peanuts. Oh, it's been pushed back, so now it's the first of so it's a week from today, actually. Cool. And then it'll be all the way till 2026 when we do a gravity assist at Earth. And so one of the things that was hard fought was they wanted to calibrate the radar instrument at Mars, because we know a lot about Mars, and this is the first time this kind of radar has been on a deep space mission to Jupiter. And so we really want to make sure that the radar instrument is working properly and that we have a calibration of it. And my friend fought for 2 months to get them to agree to do some observations when we do the gravity assist. And it's like, we are literally there. We have something, we know all the characteristics of it. We can calibrate our instrument. And they were like, no, we don't need to do that. And it's like, breathe. But she finally convinced them that, yes, indeed, this was important enough to actually do. And so we will be testing the radar instrument next week. And then, as we said, April of 2030 is when we will be arriving at Jupiter. There was a camera on in the clean room where we were building the spacecraft. That now, of course, is gone. But there are several other online resources, coloring sheets, poetry lessons, poster stickers. If you know teachers high school, junior high, elementary school. There are educational materials at all levels that you can incorporate in your science classes. So I encourage you to go explore that if you work with kids in any, in any sort of way. If you're a scout leader, if you work with a church group, school, whatever, these are available for free from NASA. And this is a QR code. I'm going to leave that up for people to observe for the various resources that we have. And I believe, yeah, I'm going to go one more, but I'll come back to the QR code. We have various social media accounts. You can follow what's going on all of these different platforms. Now I'm going to go back to the QR code and I will take questions.
Thank you, Bridget. I appreciate that's an awesome presentation. I was looking to see if anybody had questions, and so far no one's been brave enough to post one. So
That was amazing. That was awesome.
Thank you.
I have a silly question. Did that box ever had to be used, the one with the chips attached to the outside?
Oh yeah, they put it on the spacecraft.
It's up there. Yeah.
Yeah, they're going to use it to test and make sure that that when they heat them after they pass through the radiation belt, they have it test so they can test all the different batches or representatives of all the different batches.
Right. Oh my goodness, this is so cool. This is just amazing. And so they have all these things, the panel, like you said, it was inscribed with all that stuff from Earth and humans attached as part of the instrument panels, or whatever the parts in there.
The radiation.
So it gets to travel with with all that stuff, and go. Oh, this is one question I want to know. When the mission is done, does the Clipper get to go die inside the Europa? Like, does it fall or on Jupiter?
Oh no.
What happens to it? What is the plan?
The plan is to drop it into Jupiter.
Okay.
We wouldn't want to drop it on Europa because there are different levels of cleanliness for various kinds of spacecraft. So an orbiter doesn't have to be as clean as a lander or a rover because it's not landing. The last thing we want to do is go somewhere and, oh, look, we found life, only to find out that we took it there with us.
So like it would hurt the life on Europa if it actually, like, we don't know what it would do to it, right? So
we don't want to contaminate it. We don't
right.
Because you can't clean it such that there is no life forms. There's bacteria, there's spores, there's all sorts of things, and we can clean it to a certain level, but we can't guarantee that there's nothing on it.
But if it falls into Jupiter, we don't care, right? Because it's kind of a mess anyway.
It'll get baked. It'll get dissolved. Yeah. It'll burn up. It's and we can't figure any kind of life that could live in Jupiter's atmosphere, and Jupiter doesn't really have a surface. So, of the two, that's the safer bet.
Right. So, if you mentioned it, and you probably did, and I missed it, how long is the Clipper supposed to be at Europa before then like you just said, going to drop it on Jupiter itself? How long is that supposed to go?
Its primary mission is 3.5 years. They don't know how much longer it will last than that because it's a very high radiation environment. And so it just takes a beating. And at that point, we'll see which instruments are still functional, how much fuel we still have, yada, yada, yada. There's a lot of things that go into it. And they may apply for a 2-year extended mission. They probably won't apply for more than 3 years because the chances of it surviving in that hard radiation for that long is pretty low.
Cool. So if it's going to take a beating and they don't know how long it's going to last, what happens if it doesn't go the way that they planned? Like if it doesn't last as long as they think, how are they going to make sure it gets dropped on Jupiter and doesn't accidentally fall on Europa?
That's a good question.
That's an excellent question. And we can't know for sure, but we will be more conservative than
Yeah.
sporty.
Yeah. Yeah.
We obviously we monitor the spacecraft. We see how it's doing. If it starts deteriorating faster, we may have to pitch it before the end of the prime mission. But we have a good track record of lasting longer than our designs. So we're hopeful that the prime mission will go and we get some extended mission.
Does it have the capability for a controlled descent should something go wrong?
Yeah. That's, like I said, we would, unless something happened catastrophically, like, space dust came by and just blew it up, we should be able to change its trajectory to the point where it might not impact Jupiter, but it would not impact Europa. And that's the important part.
But otherwise, like if, let's say it crashed on Europa, would it just sit there on the surface of the ice? Because it can't really, it's probably not going to break through to the whatever's under the ice. More water or, we hope,
Yeah, we would hope that would be the case. I personally don't know how thick the ice is.
Yeah.
It would depend on how fast it was coming in. If you come in at a certain angle, you get a much deeper crater than you would if you came in at a glancing angle.
Right.
We would really hope that if it did crash, it stayed on the surface.
Right.
But even if it does, the water comes up through the cracks and covers a lot of the surface. So
not a good thing, right?
Not a good thing.
Yes.
That's definitely to be avoided.
Wow.
We would err on the side of caution and sacrifice additional science if we saw something bad happening, such that we might lose control of the spacecraft. That we would definitely be conservative in our assessment of when we would lose control of the spacecraft.
Wow. Amazing. That's amazing. I just, the one thing I keep on thinking back is Cassini, when Cassini fell into Saturn, right? That's the other thing, we lost it, but that was planned. They planned to have it go into Saturn. So
exactly. And for the same reason, because they didn't want it to hit Titan and contaminate Titan.
Yep.
So, but when you have a 4-year mission and you get 17 years out of it, you're doing okay.
Oh yeah. What I'm trying to think, was it the record Voyager 2 or Voyager 1, which was like the one that's still going and
both the Voyagers, yeah.
Both of them. Okay, yeah. Wow.
I mean, they got to be going long enough to meet up with the Star Trek crew and
I know. Well, that's how we make Voyager. Voyager is being that,
Exactly, yeah.
Right.
Yeah.
That doesn't happen for many years, so yeah.
But we're still on schedule.
Yep.
Right. Just so people know, we did allow an hour and a half for this panel, so it's not like we have to run off just yet. We still have time. So yeah, I know some of the other panels are only on an hour, so I just want to remind people we do have time to keep asking questions. So stick around, please, and ask questions.
This is a lot of fun.
I think we pretty much covered the two that are in the chat at the moment.
Well, sort of. So one of those was mine. So I have a little experience, working with things that are already out in space, and being able to potentially engineer capabilities that we didn't know we already had on the craft. Are there any studies that are being looked at that you might know of that go in that direction with the Clipper?
Not that I'm aware of, but then again, they've just launched and are still doing the checkout of the spacecraft. So people have been very clever in the ways that they have worked around issues on previous missions, or taken advantage of, okay, later in a mission, once you've passed your prime mission and your first extended mission, you tend to be a little sportier about what you're doing. For one of the things Cassini did, we went through plumes from Enceladus. So we're skimming like 25 kilometers off the surface of Enceladus. Think about that, 25 kilometers.
Wow.
We're 1 million kilometers away. And we're getting that accurate.
Yeah.
Just, it was nerve-wracking. I'll just tell you that. But going through the plume, you know, we were deliberately going through these jets of water and ice. And Europe is going to do some of the same things. And like I said, you get a little sportier once you've hit most of your mission objectives, and you start saying, well, we still got a spacecraft. What can we do with this?
Now, when you go through those jets, does that throw it off course a little bit? I mean, because you're making, I wonder if that doesn't.
It's not strong enough to do
Not
that.
strong enough. Okay.
It's very, very sparse.
Okay.
And the things like the dust detector has a field day. But also a dust detector usually doesn't like it when it gets water on it. So sometimes what they have to do then is heat it up to burn, to evaporate the water, because it just overflows. It overwhelms the instruments. It's like turning a camera to the sun. Yes, it needs light, but looking directly at the sun is just not good. It's just too much.
Now, the fact that everything has to be heated, that makes me think of, because it's so far away from the sun. So you have to provide your own heat, right? For all these things to happen.
Yep.
That's just amazing. It's so amazing.
Yeah. And that's one of the reasons why in the past we weren't able to do that with solar panels. But the technology has advanced to the point where we can now use solar panels at Jupiter.
Right. Wow.
Kelly actually had a question which hasn't been answered yet, that she put in chat. I don't know if you saw it, Teri, or not, but it had to do with life on Europa.
Yeah, I was just about to ask Shelley if she wanted to ask that question herself.
Sure. So Bridget, I'm one of the reasons we chose Europa was because it's a water moon, and it potentially could have life. But if we can never directly interact with it because we might contaminate it with our instruments and our probes, then how will we ever really know that whether or not it contains life?
The thing is that we sterilize landers much more thoroughly than we do orbiters.
Okay, you kind of said that maybe before, and I didn't.
Okay, so you send a lander instead of over. Okay.
Yeah, and the thing is, you don't sterilize an orbiter to lander specifications because it's a pain in the ass and it's really expensive. So you don't want to do it just to do it. And you make the trade-off. You trade off the need to do something definite with it at end of life for the cost and the effort of decontaminating it to lander levels. So
what about if you go through the geyser? Can't you get some life, like, or whatever, like contents of the geyser?
Yeah, but we don't have, I don't know enough about the dust detector to know, I don't think it's a life detector.
Like if it sucks up the whatever this stuff is and just puts it in a little thing and analyzes it, or whatever.
A miracle occurs. Actually.
Right, a miracle.
I was actually once on a mission that was trying to design a mission to Europa, which would land, melt down through the 4 kilometers of ice, and release a submarine.
Wow.
in the ocean. And it was a fascinating conference because we had people from a whole bunch of really weird different professions. There's one guy who goes into like caves and very distant regions and collects water samples and then brings them back and throws them in petri dishes with breast cancer and all of these other things to see if there's anything that would heal it, you know? So the question becomes, how do you recognize life? And one of the tests is, well, it was live before because it's dead now. And one of the tests is, it ate my lunch, where you provide it with some sort of nutrient solution, and if it consumes some of it, then okay, something happened there. But it's very hard to find life as we don't know it. We have to make guesses about what the life consists of. And if
could the lunch have eaten itself? I mean, you could say that the life was already in the lunch and it, you know, whatever that meant.
But if it doesn't come up and knock on the camera lens, it's something of a challenge to determine if something is actually life or if it's a chemical process that's happening.
Yeah.
There was a lot of when Viking landed on Mars, they had several experiments that they got very inconclusive results on, and there was some whisper thinking, saying, "Oh, we may have found life," and it turned out it was just a very hydroxynated mineral in the soil. And it mimicked some of the activities that life would do, but they were able to determine from other tests. That's one of the things about having multiple instruments on the same spacecraft, is you get measurements of different things on the same target. And for example, one instrument will say, well, it's either composed of this or it has this size particles, and that instrument can't tell any more than that. But another instrument might be able to determine which of those is, but it wouldn't be able to do that without that data to work on. So the synergistic effects between the instruments makes the data set much more robust and much more valuable. I've always often said that the Cassini data set, with its 13 instruments and 14 years at Saturn, is going to be in doctoral dissertations for 100 years. People will be analyzing not just one instrument's materials or data, but comparing one data set with another. I did some of this work when I was in grad school. I took Mariner 9 data, and I took visual data and infrared data, and was able to determine that the residual polar cap of Mars is CO2 ice, because I was able to determine that the ice never got above the sublimation temperature of CO2. So it was coming off, but there was still CO2 left, but you couldn't tell that from one instrument's data. You had to use both sets of data on the same target to be able to get that information. And so that's the advantage of having these multiple instruments.
Now, you said 14 instruments. How many were on the Cassini?
That I think there was a dozen.
It does 12. What about, are there more instruments on this mission, on the Clipper mission, than?
No, I think
we know? Or is it the same type of instrument?
It's very similar types of instruments.
Right.
I think it was like 10. We should go back to the beginning here.
Because I'm just wondering if there's if it's a progression of more science, like more ability to do more now that we advanced a little bit, or?
It's more. It comes more from the higher fidelity of the instruments. The instruments themselves are better.
Oh,
higher
okay. Okay,
resolution
that makes sense.
and things of that sort. Our cameras are better, you know,
Right.
we have more filters, we have more wavelengths that we look at, that sort of thing. The dust
Right.
detector is more sensitive. So it has more to do with that than, although in this case, the reason instrument, the ground ice penetrating radar, that's the first time we've had that instrument in the Jovian
Oh.
system. So that's gonna be groundbreaking. We're gonna find all sorts of things that we never knew before because
Right.
we just didn't have this data before.
Is that going to be like a little drill of some sort as it goes in and penetrates?
No,
You
no,
said,
it's one of
what
the
it
remote
is?
sensing instruments. It's what
Oh,
it
so it
does-
doesn't touch. Okay.
Right. It sends radar waves down to the ice and
I
it
see.
penetrates to a certain level. And you can tell from that, you can see fractures in the ice, you can see layering in the ice. And if the ice is thin enough, you can see all the way to the water.
Oh, I get it now. So there's 5 instruments that go make contact with it in situ. Does that mean it's literally making contact or not? Or is it just
It's
close?
measuring what's around the spacecraft. So the dust
okay.
that's around it, we're not touching.
Right, because you're not touching Europa. I forgot. Okay, you're right. Wow, this is great. This is amazing.
Any other questions?
This is just curiosity and showing my lack of information about space in general, but it's mentioned several times in the presentation that they have to do certain things because of the high radiation around there. Is that typical around like all the, I mean, obviously I know we're protected on Earth to a high degree, but is that typical of all the planets and moons and stuff outside?
It depends. Jupiter is the big bully. It has the most harsh radiation environment. Saturn is almost as harsh, but it also, there's also the issue of the interaction between the magnetic field of the planet with the solar wind. And for example, with Cassini, we actually orbited at a distance which took us out of Saturn's magnetic shielding and out into the solar wind. So when we were between the sun and Saturn, we were not covered by Saturn's magnetic field. So we were going in and out as we went around. I don't know enough about Europa Clipper's orbit to know whether it's doing the same thing at Jupiter. So, you know, it's different environment. If it's always in the Jupiter environment, it's going to be harsher than if it gets out of that and goes into the solar wind, because the solar wind would have dissipated so much by the time it got there.
Thank you.
Somebody just asked in the chat, they said, how likely is it that Europa could get hit by an asteroid on its journey? And does it have something to protect it from getting hit by things?
Jupiter is what protects it from getting hit by things. Jupiter, as I said, Jupiter's a bully. It flings things about, and so anything that would be coming for Europa, chances are that the gravitational field of Jupiter would suck it off and either fling it out completely or bring it in. The chances of it being hit by something of that sort is fairly low, because Jupiter is so much heavier and it would just bring it. It would deflect it.
Yeah.
It's a good question.
Very cool. Very cool.
Okay, well, we have about 10 more minutes left. So does anybody have any? Oh, somebody. Okay, one more question. What about the asteroid belt? Is what the next question was.
The
I'm not sure. Do they mean like, would it get in the way? Does it interfere? What do we have to worry about it? Do we have to worry about it? Okay.
The asteroid.
Yeah.
Sorry.
Yes.
One of the questions that frequently gets asked is, do we have to worry about traveling through the asteroid belt to get to Jupiter? If that's the question, the asteroid belt is a lot thinner than in Star Wars. And so we've actually, anytime we go through the asteroid belt, people are excitedly looking, oh, are you going near any of these that we could take some pictures as we're going? And in this case, no.
Because the distances are so far apart between those pieces that people think it's like you're dodging rocks, but no.
Yeah.
Right?
Yeah.
So it's not like rush hour traffic on the 405.
Yeah.
God, no.
Dodging. Okay, yeah. Got it.
So
Okay.
if the concern is whether the asteroid belt is providing ammo for Jupiter to fling around, it's been there for 4 billion years. It's anything that was going to be thrown out is going to be thrown out.
Has already had that happen, right?
Yeah.
Cool.
So is that even considered in calculating the launch window, or is it just kind of neglected?
It's not really something that we worry about. They do, like I said, they do look at those numbers and look at the larger asteroids, but even if after we launched, we just determined that there was an issue, we would just plan maneuvers such that we would slow it down or speed it up enough. It wouldn't take much to make it miss.
I keep on thinking an analogy would be like, if we're going to launch from Earth to go to Mars, we don't have to worry about colliding with the moon because it's so, it's out there. We don't have to go, oh no, the moon is hit us.
Yeah. Yeah. We're more likely to hit something in orbit around Earth, like
right.
other satellites.
Junk. Right.
Okay, so when will the solar panels be extended? During the journey or only once it gets to Europa?
They're already done. They deployed them, and that's one of the things that they're going to. They wanted to deploy them before they got to Mars, so that because the radar, the ground penetrating radar antennae are on the solar panels. They're on the bottom. Let's see if I can show you those. There's these four. There's two on this side, two on the other side, and then there's these four, which are longer. And those couldn't be deployed until the solar panels were deployed.
Oh.
Those are the things that I said we wanted to test at Mars because they've never been flown to Jupiter before, and we want to calibrate them because we know what we see at Mars. We have ground penetrating radar at Mars, so we know what we've seen already. We can calibrate these instruments, make sure they're working correctly. So we had to get it all deployed, and besides, it needs the power.
So calibrating the instruments at that point helps to ensure that you understand the answers you get at Europa and have some confidence in their accuracy.
Exactly. Exactly.
Got it. Okay, somebody else asked. Yeah, people are asking questions. Cool. How do they avoid all the traffic when they launch?
The air traffic in the sky, it's a challenge. There's a lot of space debris, and there are people whose sole job is to track everything that's in orbit currently. And
oh wow.
they have to.
There's a lot of junk up there, yeah.
There is, and a lot of it's dead, so we don't have anything. We don't have a way to ping it. We have to.
There's a show. Was it on HBO Station 4? Something like it's a comedy space about a ship. What was it called? Something Station 423 or
oh no, it had oh no, I was thinking the one with the 5 in the name of it.
Or maybe 5. But I'm thinking of a bunch of poo in the orbit around the ship. You know what I'm talking about. Many of you have seen this.
Yeah, the one with Hugh Laurie, I think.
Yes, yes. Hugh Laurie is the
uh-huh.
captain who's not really a captain. He was just like, you know, an
Yeah, I
actor.
cannot remember
And
the
then
name of that one, but
they
yeah.
launched like all the poo and it's like falling the ship. So I'm thinking,
It
this
just
is
follows their
just, you
ship
know,
around,
Earth
yeah.
has its own poo belt.
Yes, yes.
Point. Oh God.
Something like Hyperion 5 or something like that.
Yeah, it's something. Yeah, it's some weird little name, and I can't remember. But there are numbers in the name, so
Yeah. Okay. So,
anyway,
well,
it's a fun show.
since we only have about 5 more minutes before we have to let everybody go anyway, and nobody else has posted another question, I suppose we can call it an end. And thank you again, Bridget. We really appreciate it.
Yeah.
This was absolutely fascinating.
Thank you so much. This was
Glad you
great. I
asked
mean,
me again.
I learned so
And-
much stuff about Europa. This is going to actually help me with stuff as I'm writing. So thank you.
Excellent.
And pass our thanks along to Trish for letting her borrow your,
Yes.
borrow her presentation.
Will do.
Thank you.
She's also the
Awesome.
one that put myself and my daughter up during the fires.
Oh, all right. Awesome. Yeah.
Our house is fine, but we were evacuated for 2 weeks, and so we lived with
Oh.
her for 2
Wow.
weeks.
That's very scary, man. Very
Yeah.
scary stuff. But I'm glad that your house was fine. So, woohoo.
Thank goodness. Thank goodness.
Yes.
Yeah. All right. Well,
Thank you,
thanks
Bridget.
everybody. And our next panel is at 8:30 Eastern, and it is I forget. So let me check really quick. We'll be talking about the special editions of the books, and several of us have copies of the 2 that are out now, so you can see what they look like.
Yes.
So come
Yay.
look. Okay. Thanks again. Have a great night, Bridget.
Thank you.
Good night.